Okay, good. Yeah, thanks for the introduction. It's actually true about drinking the butter. So I hope to explain to you something about the first stars that lived very early in the history of the universe. These stars were likely very different from the sun, but very important for us. And I'll talk to you about the properties of the first stars, how to find them, and particularly on how they influenced the universe later on. And I will paint this story using this diagram or this table. And I hope it's familiar to some of you. You may use it during your daily life. Or maybe if you're not a chemist or a physicist, you may have seen this for the last time during your chemistry exam in high school. This is a periodic table of elements and shows basically different elements that are the building blocks of atoms and molecules. But I particularly like this version because this version shows for each element, the color shows where this element was produced throughout the history of the universe. And now I'll guide you through this. So the first thing to notice is that only two elements and a little bit the third element, only two elements are blue, and those are the elements that were produced in the first few minutes after the Big Bang. This means that when the universe formed, a few minutes after the Big Bang until a few million years, the entire universe, at least the universe that we consisted of hydrogen and helium, and not of other elements like carbon, nitrogen, oxygen, or iron that are very important for planets and for life to develop. And all these elements that are heavier or more massive or larger than hydrogen and helium are what astronomers call heavy elements or metals. All these elements have been formed in stars, and I'll guide you through a few different kind of processes that form these elements. So these yellow elements, the most important one is oxygen, that's the most abundant. These are produced when massive stars that are much larger and more massive than our sun, when they enter lives, they explode in events called supernovae. And supernovae conditions are very extreme, the temperatures are high, there are a lot of high energetic particles traveling around, and in these conditions, heavier elements can form. And these elements are just these ones. You can see that carbon and nitrogen, C and N, also are produced differently by dying low-mass stars, similarly to more rarer elements. These names are much less well known. The green ones are produced when stars that have quite normal mass or similar to the sun, when they enter life, they expel their outer envelopes and enrich the gas around them with winds. So they don't explode, they just do it more gradually. And then there are also more complex things going on, such as merging neutron stars. I won't discuss this in detail because I think there has been an entire Astronomy on TED talk about these objects. But these are important for example, for gold, AU number 79, if you can see it. So this picture is actually not only theoretical, there are also observations. And I'll show you observations from the Hubble Space Telescope, from a star that was first found in 2002. That's because it suddenly got much brighter, and you are seeing a movie based on images over the last 13 years. And you can see that there is some gas flowing away from the star. This comes from the outer layers of the star and contains many produced heavy elements such as iron and carbon. And it's really blown into the universe away from where it came from. Out of this gas, eventually new stars and planets will form. And this is also what happened in the very distant past to us. We basically formed out such a stellar remnant. Another kind of remnant is, for example, a supernova remnant. This one, you can actually see it moving a little bit, also based on images taken in different years. This is called Tycho supernova, because this was a supernova observed in roughly 500 years ago in 1572 by the astronomer Tycho Brahe. I think I pronounced that wrong probably. But this was actually a very important supernova because it was the first time in Renaissance that a new object appeared in the sky. And this really changed the way we look at our place in the universe. So these supernova, besides influencing actually the gas around them, they also influence our understanding of the universe. So as I said, the stars that are responsible for the majority of heavy elements were much more massive than the Sun. So the Sun is shown as the small orange dot here. It has a temperature, an effective temperature about 6,000 Kelvin. But stars that were more important for chemical enrichment are stars like this, much more massive than the Sun. Because they are more massive, they consume their fuel much faster. It's basically like having a big American car, it consumes much more fuel. But these stars live much shorter. And if you compare, for example, the lifetime that the Sun will have, which is roughly 10 billion years, to the lifetime of such a star, if the Sun would live a year, such a star would only live for one night. So these are things that are occurring on quite different time scales. This process of stars forming and forming heavy elements must have started at some point, because after the Big Bang only hydrogen and helium existed. And the stars that were first formed, that consisted only of hydrogen and helium, likely were much more massive even than the most massive stars we can see around us today. And because they were so massive, they were very large and also very hot, so roughly 100,000 Kelvin. So they lived even shorter. If you compare it to the same analogy, they only had one evening, basically. And they also, because they are so massive, one day they end their lives as explosions, but their center part actually collapses into black holes. These black holes have a mass similar to the mass of a star, but eventually, when many form, they can combine and form supermassive black holes. And that will be the topic of the talk later today by Ayush. So these first stars, if you place them on this diagram, they consisted only of hydrogen and helium. But they have not been observed in the universe yet. So why is that? It's likely because they're just very hard to find. So because these stars are so massive, they lived very shortly. So they have formed very early on in the universe. So if you want to find them, we have to look back in time by quite a long time. Because they live so shortly, they also enrich their environment, or they pollute their environment very rapidly. And out of that polluted environment, second generation stars form, and they will rapidly outshine first generations of stars. So the time window in which you can find these stars is short, and they are also very rapidly outshined by more normal stars. But instead, so finding them sounds maybe very difficult. Instead, when I started my PhD 4 years ago, I'm actually almost finishing, we found a galaxy that we named CR7. I will explain that galaxy later. And this galaxy, I'll explain the name later. This galaxy back then showed the best evidence that we were actually seeing such kind of stars, so first generation stars that formed early in the history of the universe. So this galaxy consists of three different clumps. We named these A, B, and C. And you can also see some green glow around this. And this is heated hydrogen gas that's heated by the star. These three different clumps. Because this galaxy is very far away from us, we don't see it at very high resolution. And if we would be able to see this with a much bigger telescope, it could perhaps look like this. So these few pixels that you see actually are a large combination of stars and gas around this. So keep that in mind. So of course, if you ask an artist, he can make a very nice picture that looks like this. You can identify three different components, but now you can actually see the stars. In between, the stars are very hot and therefore very blue, so you see this blue gas around it. So why did we name this galaxy Cosmos Redshift 7? So Cosmos is basically a name for the location in the sky. It's a part of the sky that we call Cosmos. And Redshift 7 is basically a measure of its distance. So the abbreviation is CR7, and that actually is very useful. Because, for example, if you advertise this meeting on Facebook, you can actually, like I use advertise, tomorrow we'll discuss CR7 and TGSS 1530 plus 1049. People don't really come to that IE, so you definitely need to shorten it. And someone agrees with me as well. Also, if you name a galaxy CR7, you also inherit a large fan base, so you really don't have to worry about making this galaxy famous. The internet will just do it for you. It's also a way to make audiences learn something about astronomy on places where they don't expect it. Sometimes that has bad consequences. For example, the newspaper, the last one I showed, wrote it's an exceptionally rare object, it's true. It's by far the hottest we observed at this stage, but we didn't refer whether it's the galaxy or not. Anyway, so why is this galaxy so interesting? So we're seeing this galaxy at a distance of 12.6 billion look-back years. So we see this galaxy when the universe is only 800 million years old. The universe is now roughly 14 billion years old. So this is really something that we see in the first few hundred million years. There are other galaxies known that are at such high distance, even more distant objects. But this galaxy is among the brightest, meaning that we can study it in a bit more detail. And it's also the hottest object. And first generation stars were very hot, so this is a good candidate to look at it in detail. So to really learn what kind of stars are in this galaxy, you cannot just take photographs, like the picture you see, but you need to employ a technique of spectroscopy. Spectroscopy is basically a prisma that I think everyone has sometimes seen, some people put in front of their windows. But we used a very advanced prisma, the X-shooter spectrograph on the VLT in Chile. And if the X-shooter spectrograph observes the sun, for example, it sees light at each different color. So this is the light split in all the different colors, and this tells you something about the properties. When we observed CR7 with X-shooter, we actually only saw light in two very distinct wavelength regions. And these different regions, they correspond to hydrogen, and this is where we looked for, so it's obvious to find it. But there's a lot of it, and it's bright. But surprisingly, we also found helium. Of course, you can argue how good is this detection, but it seems to be there. But this helium really indicates that the temperature of the stars is very high, so that there's something hot going on. More surprisingly, if you find helium, you also expect to find carbon and oxygen, but at the locations where we would have seen it, and we would have seen was illustrated in the black line, we don't see it at all. Especially for carbon in these kinds of observations. So this indicates that we could be seeing a first generation galaxy, which is very, very exciting. Because now we found it, we could of course look at it in a bit more detail. But because this is such an important thing to find, we of course need to test it in every different possibility. So instead of using Hubble Space Telescope and the VLT, what we did before, we actually observed this galaxy with ALMA, which is the Atacama Large Millimeter Array, which is just this nice collection of satellite dishes. This is located in one of the driest places on Earth, the Atacama Desert. I think they could have located it in the Netherlands the last few months. Anyway, the Atacama Desert is even drier. So with ALMA, we did detect carbon in the gas around stars. So before we actually mostly looked at the stars themselves and the gas close to stars. But with ALMA, we were able to look at gas that's a little bit further away from stars. And we got a detection of carbon, and that's shown as the orange contour lines in this figure, and the original image by the Hubble Space Telescope is shown before. So ALMA actually learned us that by looking at the galaxy in a different way, there's actually still carbon present, meaning that we're not seeing the first generations of stars, because metal enrichment has already started a little bit. Of course, you can only fill in carbon now in this diagram. Ideally, you fill it in completely. Most elements are very hard to see in distant galaxies, but in the future, we hope to at least see nitrogen and oxygen and perhaps magnesium and iron, to learn a bit about the kind of stars that have been living in this galaxy, in the early universe, because then you can also indirectly constrain and learn about their properties. It also likely means that if we really want to find the first generation of stars, we need to look at even higher galaxies that are even further away from us. Eventually, this may be possible, this will be possible when the James Webb Space Telescope will be launched. The launch date is subject to changes, but in principle it's an ideal instrument. It's by far the best. Once it's launched, by far the best telescope to look at these kind of objects in detail. It will have a field of view, so the sizes of the photos you can get for spectroscopic images, so splitting the light, are basically the same size as galaxies, so it's really well designed, but we still have to wait, unfortunately, for it, so you really have to stay tuned, but slowly we'll get there. And so this was my talk. I'll just leave you with my summary, and I'm happy to answer anything.